Hi, well, good afternoon, everyone. Welcome to this afternoon's webinar on industrial strength physics-based battery modeling. My name is Pete Keevill, and I'm leading the commercialization strategy of physics-based battery modeling tools within Faraday Institution. So in this webinar, we'll be discussing the potential benefits of wider industrial use of physics-based modeling. Facilitated by our new battery parameter exchange standard, of which we're going with the acronym BPX, which we're launching today. Before we get too far in, just some Faraday House rules on webinars. We ask you to be fully present, avoiding the distractions of multitasking. Hopefully we're going to be saying something interesting. Please use the Q&A box in Zoom to post questions, and there'll be question answer session at the end. With myself and all the panelists. Please respect all the contributions that are made during this session, and please don't say anything you might regret later. This is essentially a public session. We are recording it and using it for later, so please respect that and make sure you're not sharing anything you shouldn't. So I feel obliged to explain the title. So what is industrial strength physics-based battery modeling? It's in quotes, which immediately attracts some suspicion. So to answer that, I need to wind back about a year to when I first started working on battery modeling. My work was involved around the two physics-based simulation tools, PyBAM and Dandelion, that were created as part of the Faraday multi-scale modeling research program. So PyBAM being an open source tool and Dandelion being optimized for sort of heavyweight applications, if you like, potentially including hundreds of cells. So I'm new to the battery industry. So I asked to set up a number of meetings with industrial partners just to get their perspectives on physics-based modeling. And pretty soon within all those meetings, everyone started talking about models and the difficulty of getting accurate models that they trusted and believed in. And frankly, I was quite surprised that that was such an issue. It almost seemed to be a sort of structural issue across the industry. Anyway, so based on those initial discussions, I've come up with these 4 points. So what is industrial strength? First of all, is accurate. That's what physics-based is bringing. Accurate in a broad range of scenarios. And accurate, to put a rough number on it, I suppose we're generally talking, within 1% of a real cell, within 1 or 2% in that broad range of scenarios. It's fast enough for virtual prototyping, and that number, when we sort of dug in and explored further, that number comes out as sort of 10 times to 100 times real time. So that seems to be the useful range for in simulators for virtual prototyping. It's trustworthy. A number of people commented on whether they really knew what was in the model, what behaviors were actually modeled. And that's so this issue of trust came up a few times. So whatever it is, whatever we do, it needs to be clear what is modeled and what isn't. And finally, plug and play. We want a model that will just drop into our simulator and work. We don't want to have to do manual tweaks and fiddles and compensate for the parameters that are expressed slightly differently or the units are a bit different. So that was the sort of story that I came out with after those initial meetings about what was industrial strength. Some of these issues are solved by simulators. Fast is certainly a simulator problem, typically. But other areas were less clearly directly related to the simulator, much more around the model. And there seemed to be a need for something else, some guidance around what a good physics-based model would be, some kind of template or standard. So in many ways, we sort of reflected on this and repackaged some of the research output of the MSM program, the multi-scale modeling program that delivered PyBAM and Dandelion, and presented this BPX standard to define what the parameters should be. It makes no sense to talk about the parameters without talking about the equations the parameters are used in, and give some guidance around how those parameters are extracted and how the model itself might have been validated, really without the goal of forcing a particular way of doing it, but just to encourage an informed conversation between model vendor and user as to how those things are covered. So we worked away on this for a few months and have launched a shiny new website at www.bpxstandard.com. So do please go and have a look at that. I think it went live this morning. So on that site is a package of information you can download, which is the specification document for the standard itself, which is quite a concise piece of work. We arrived at the conclusion that a JSON file format would be most useful and flexible in this application. So we've got a definition of the JSON schema that we're using. And there are some example cell models that About Energy have produced for us, which you can go and have a look at. And if you have access to PyBAM and Dandelion, you'll be able to use them shortly. We also have a Get Involved tab there. So we're very much interested in your feedback. And as you'll hear later, we have thoughts about where this whole process will go. So we'd very much like to hear your feedback and be interested in your participation as we move along, but more about that later. I should at this point give a profound thanks to Robert Timms of the PyBAM team and Ivan Korotkin of the Dandelion team, who've done all the hard work in terms of actually putting together these definitions, and Martin Robinson also for the JSON schema. So thank you to all of them. They know far more about modeling than I ever will. We won't be going into a lot of detail around the standard in this session. There's another one following on January the 11th, and that is the technical deep dive, where you'll be hearing from the people who actually wrote the details of the specification. So that's the time to come back. So meanwhile, we here today are going to pull back on that question of what does industry, what can industry benefit from much more widespread use of physics-based modeling? And to that end, I'd like to introduce our panel. So first, Dr. Monica Marinescu of Imperial College London, and also the Faraday Institution Multi-Scale Modeling Project. Welcome to Monica, thanks for joining us. To Rob Millar, who is Head of Electrical at what was known as Williams Advanced Engineering, but now is WAE, following an acquisition. So welcome to you, Rob, and thanks for joining us. Next to Pete Bishop, who was part of Civil Power Systems, but they've been acquired too, and he's now the CTO of Gridserve Technologies. So with a very busy industry, as you can tell by the number of acquisitions going on. So welcome to you, Pete. And last but by no means least, Steve Farmer from AMTE Power. Steve is the Innovation Director with AMTE, one of the UK's leading battery manufacturers. So to give you that question, we've laid out the ground for what industrial strength physics-based modeling would look like. So I'd be interested in what your thoughts are on the win for your particular business. What do you think you're going to win through more extensive use of physics-based modeling, certainly than you do at the moment? So perhaps if I could start with you, Rob, what do you think of the win is for WAE?
So I think the win is actually, on several sort of levels. I think the first one's rather practical. So I mean, if I want to find a cell that's sat in China today, and I'm quite interested in what it looks like, it takes me some time for my procurement people to sort of negotiate to actually get a cell sent. Then it has to make its way over the sea or through the air to me. And then we start going through a whole series of testing activities to actually discern what this cell does in reality. And what a physics-based model does is it shortcuts that entirely. I mean, we can actually start to look at what the real genuine performance of a cell is without that need to go through that testing loop and have all these sort of convoluted sort of procurement activities that we always have. I think the second sort of thing that it probably gives us is, traditionally, if we were able to receive a model, it would be an equivalent circuit model of some sort, and that is much more difficult for us to interrogate. Typically, it's a black box model, and we would have difficulty in essentially, modifying that to sort of show the through life or the degradation sort of performance of a cell. And so that becomes a problem for us. So white boxing the model, as we are sort of proposing to do here, gives us much more information. It lets us observe the internal states of, every element that's within the cell, and that gives us, much greater sort of possibilities in terms of extracting performance from that cell. I guess one of the other things we get is, if we have a good reduced order physics-based model, then we're able to take that, create a simplified version, put that into algorithms relatively simply, rather than going through, a prolonged process that we have today. Degradation is already alluded to, enabling us to model degradation just brings a whole host of benefits. It allows us to understand, what the real world performance of the cell will be, but it also allows us to adapt performance in use. We can see what the degradation methods are that are occurring. We can correlate those with what models tell us, and so, you know, so rather a long answer, but there are very many benefits for us in this.
No, it's fascinating to hear that perspective on, you know, the transparency, the power of virtual prototyping, the accuracy. They're all coming across. So that's great. Thank you very much. So perhaps the same question then, moving on to you, Pete. You know, obviously your work with Silver Power was quite a diversity of different things, with a lot of kind of battery fleet measurement and management and estimation, and really trying to optimize the performance of a battery fleet, and obviously some work with UK sort of smaller vehicle manufacturers, but niche vehicles in terms of modeling and working. And now with Gridserve, perhaps you've even got the large power system energy storage stuff there as well. So a big diversity of perspectives there. But from your point of view, perhaps what do you think of the wins for the Gridserve organization now in moving to more extensive use of physics-based?
Well, as you say, Peter, we work with a number of smaller niche vehicle manufacturers who typically don't have battery expertise extensively in-house. And we've been supporting them with modelling batteries for powertrain design, developing digital twins, etc. Really to determine things like BMS calibrations, but also with the power of modelling, we can look at, you know, what's happening internally within the cells, particularly looking at fast charge limitations. But really for them, it's a case of using modelling instead of building multiple expensive prototypes. So we can iterate through a number of different cells and topologies, particularly where they're integrating them into the vehicle chassis. So thermal modeling things comes into that as well. So it's really reducing the time to market and reducing the cost to develop these niche vehicle platforms. The other thing I'll just say in relation to that is historically we've had quite a lot of difficulty getting hold of good cell data from cell manufacturers. So having a common standard will make it a lot easier for people to understand what sort of parameters we need to do that modeling. So I see that as a great benefit of having the standard. You mentioned our sort of, you know, more recent activities. Now we're part of the Gridserve group. Gridserve are a large electric vehicle leasing company, as well as running the largest charging network in the UK. And so they've got a lot of interest in asset valuation of lease vehicles. And so going forwards, particularly being able to model and understand degradation and the behaviours that affect degradation on those leased vehicles will be instrumental in determining the residual value of them and going into second life applications. So it's another area we're going to be applying modelling into.
Yeah, very good. Fascinating stuff, I think, all around. I mean, certainly the degradation question come up a few times here, and that whole life cycle, whole life use, and what performance we can expect, and therefore how we can guide the BMS system or whatever to optimize it as best we can. And that's yeah, certainly not something we address immediately, but it's sort of kind of on my list for where we might get to, hopefully in the fairly near future. So moving on then, coming on to you, Steve. Obviously, I imagine that within AMTE you're doing something like this already in terms of the development of the batteries, but in terms of being able to perhaps expose more of that to some of your customers, you know, some might see that as a risk for a battery maker, but do you see benefits and wins in terms of engaging customers and just resolving problems faster, working with customers through this kind of approach?
Yeah, so certainly. So I mean, at the moment, we're using physics-based modelling to sort of reduce our time to market. So the sort of development process involves a number of iterations, and that can be relatively costly. We're currently in UK BIC scaling up our ultra-high power cell. But one of the things that physics-based modeling's provided is the ability to short-circuit some of that iterative process. And as a result, we've been able to bring forward the introduction to, or the potential introduction to market through our mega factory. But at the moment, we've been involved quite a bit on, particularly on thermal modelling, and that's both the sort of ultra high power cell that we've been developing, and particularly working with integrators, OEMs, on a sort of integrated electrochemical thermal coupling model, and that's the area where we would see that there was collaboration and interaction between organizations, and particularly if we got the right model and the right setup, we would collaborate and share models, again, possibly through the PBX, for that particular application. I mean, in the future, and as Pete said, we've also been looking at degradation models, life models, and again, the idea is to provide that sort of information to third parties. And also, we've more recently been involved in using the models for sort of supply chain evaluation. So one of the things that we found is that the market now is getting quite tied up, particularly in terms of material supply as well as cell supply as well. So we've been using it for rapid evaluation of alternative suppliers, and again, we can plug that in to see what maybe the downstream effects are on life and degradation.
Okay, yeah, that's quite a diversity of uses again, but this collaboration element with customers and partners. I mean, you mentioned particularly, I think, thermal there. So that's probably something we'll be talking about in the future. But that's an interesting sort of driver for where we need to get to on this. But yeah, thank you for that. And turning to you, Monica, finally on this question. I mean, you've heard all the answers from our industrial speakers. So from a research perspective, from a theory perspective, I mean, is that everything you expected to hear? Perhaps a few surprises there? Anything that perhaps you want to point out at this stage? There might be other benefits that haven't been talked about so far.
Yes, thanks, Peter. I think first of all, it's really exciting to be sort of doing research in this time, because I think for a long time, obviously on the academic side, we've been convinced on the power of producing physics-based models, but it's only very recently, and with the help of the Faraday and such initiatives and the multi-scale modeling, that we really have taken out this type of models from the academic silos that only the sort of maybe most boring looking academics are interested in, and brought them to a conversation with industry, where we are at the point where we can say, yes, these models can do some or many of these things, can tick some of your boxes, Peter, about maybe their broad range of applicability and relatively fast for the industry to see them as palatable solutions to their problems. So I think this is very exciting, because we're now all of a sudden not talking just about electrochemistry of batteries, but we're bringing in those large systems considerations, cooling scenarios, warranty considerations, supply of materials and how that affects the material properties and then the cell properties. So this whole engineering, electrochemical grouping of efforts. In terms of what industry says and needs, I think you've invited all very sort of educated industry representatives. They know very well what they are talking about, and indeed this is very much the direction in which the tools are going right now. So the idea of a physics-based model is directly linked to what we think matters in terms of causality between what happens inside and the performance. And this is beneficial in two ways. If we are correct, then we have all of these functions and utilities. We can test cells before we put our hands on them. We can test small changes to cells in materials or form factor without building them. This brings huge gains in time and money. On the other hand, if we are wrong, we find that out very quickly, because if the results in experiments are showing us something else, we know we have to go back and change the mechanisms that we have included. So there's a lot of benefit we gain from working with industry on these models in terms of real life applications in those systems and scenarios of operability that are very remote from both what we would do in the lab and from what maybe a cell designer would do for experiments to put on the spec sheet. So maybe something that hasn't been brought up, but I'm sure it's sort of at the back of the mind of many of the industry partners, is when a cell comes with a spec sheet, the reason why they would need to undergo so many extra experiments is because they don't actually have enough information to know how a battery will behave under the inhomogeneous conditions that they are going to use them in. And this is also something that the model enables them to do. So in terms of applicability of such physics based models, absolutely using them on some cells under different conditions, thinking about how a different cell that hasn't yet been built might perform, thinking about faster experiments, and obviously a lot of the discussion is about degradation. This is because everyone is interested in not just building the best beginning of life system, but end of life. And everyone knows now how path dependent the state of health evolution is of battery systems. And so it's almost in hindsight apparent why you would need a physics-based model. You need to have all of those causalities coupled together in order to be able to retrieve the effect of the various ways that they may be used, either because of the driver or because of your cooling choices or because of the packaging choices inside the system and so on. And it's what multi-scale modeling is very much focused on, looking at how degradation mechanisms coupled in 3 dimensions with thermal effects.
Yeah, well, there's true virtual prototypes come through over and over again about having something that really is representative of what the real physics and chemistry is doing, and that's, you know, just so much streamlining so many different things. Very good. Well, thank you all for that first question. My second question will spring off kind of almost from that looking forward. The comments on the end there, Monica, and I think everybody's alluded to where we might go next. So in our view, this is very much the first release of BPX, is get it out there, get some feedback, get some value, hopefully democratizing the use of physics-based modeling. I think you pointed out, Monica, that our users here are very expert, but you know, we want to open up benefits of physics-based to companies large and small, and hopefully that's another thing that BPX can help with. So it's very much the first release, and we have some things we thought about but haven't put in yet. So things like 3D thermal modeling, degradation, everybody's talked about several times, but that's certainly absolutely on the list. Perhaps things like interfacing between the battery model and other design tools, some kind of co-simulation interface when we're talking about thermal transfers and thermal exchanges. Then is there something we need to think about there? Some element of the standard, maybe things like actual fault models. Another reason one of the companies I was talking to was talking about the need to do so much testing is they're trying to explore all the different fault model options and how the BMS would handle that. So there's a few different things we could do. I think this also, looking into the future, drags up the question of, well, who decides what goes in? Faraday is not a standards organization, Faraday Institution. We have put this thing out, we've pulled a standard, but we're not a standards body. The lessons for other industries are that companies coming together to mutual advantage is what drives standards together to meet changing needs and technology developments. Part of my job looking into next year is developing some of the ideas around what such a standards development organization might be. So if you'd like to get involved in that, or you like what you've heard, the sound of what you've heard so far, then please do contact us on that and we can get you involved in the conversations. So let's imagine that this is the first meeting of our new standards organization, and we're getting onto the table the things that we'd like to see coming into the next release of the standard. So perhaps if I could start with you again, maybe Rob. What are the top priorities you think? Where we are today is a kind of a virgin cell. There's not degradation modeling in there yet. There's some thermal modeling, but it's not 3D detail, for example. Maybe none of those things are what you're concerned about. But I say, in terms of where you'd like to see, what are the priorities, I think, and what happens next in terms of going further with this modeling standard?
I think the point that probably Monica's just made is that we are actually at the start of something here, and what we've done is we've written down the things that we know today, and the rest of it's sort of, you know, probably a lifelong journey for most of us. You know, what we know that's important today is probably what we've already written into the standard, and what Monica and our colleagues will find in MSM over the next few years, you know, will become stuff that becomes relevant and goes into the standard in later years. And I guess that is just the nature of learning and continuous development, isn't it? So I think, you know, from an industry perspective, you know, I think all of the goals that we have are known. I think what we don't have actually is all of the parameters which deliver to those goals known as yet. But those will be the subject of research, and as that research sort of throws them out, then they will come towards us and become adopted as part of the standard. I think probably there's some other things to do with the standard that we haven't, you know, maybe really fully considered yet. So I think, you know, how we've actually arrived at some of the numbers that we'll put into the standard is a very important sort of subject. So standardizing the method by which we define something. I know that you know, in academic spheres this is already done, but how do we ensure that the sort of companies that we deal with and are producing these models for themselves are giving us something that's actually conforming to that too? And so actually having a standardized method of, you know, coming up with the numbers is very important to us. And then, you know, I think other developments are really around, you know, in research, the number of use cases perhaps is sort of quite limited. So you're looking to standardize, test things at certain single temperature, and are there sort of variances of models that we require in order to deal with sort of changing parameters that occur within the cells, while we respond to a sort of slightly difficult or different and changing physical world. I think those are interesting topics for us.
Okay, well, I'll come to Monica on the end in terms of what's coming next on MSM2 from Faraday. But interesting that that's you brought at that point in terms of where to go next, still being defined by research, which is certainly my impression of where we are on a complete story on degradation modeling. Okay, very good. Well, I'll move on to Pete then. Same question to you then, Pete, in terms of you know, what are you lobbying for in terms of where the standard should go in its next release?
Thanks, Peter. It's largely around the sort of two areas you've already mentioned, actually. One of the biggest areas we see the challenges in is in the thermal system design, particularly in achieving, you know, uniformity of thermal conditions across all the cells in the pack. So the ability to have, you know, cell parameterization that supports full 3D modeling at pack level, and this is particularly challenging when we're doing cell to chassis, which we are with some of the more innovative niche vehicle manufacturers, because we have to take into account, you know, the full 3D CAD model of the chassis and the pack design as well, and all the thermal paths through that. So it becomes quite a monster in terms of simulation. And then the other one, which yeah, Monica will know well from the conversations we've had, is around degradation modeling. We've got a big multi-year project running with an OEM to actually measure degradation on in-service fleet of vehicles over many years. And what in the course of doing that, we've got over 2.5 million miles of data now. We've collected a lot of information on different drive cycles and charge profiles that these vehicles are subjected to. And what we'd really like to be able to do is model new pack designs, apply those drive cycles and charge profiles to them, and understand then how those packs are likely to degrade through their life cycle. That's particularly important because of the impacts on obviously vehicle performance, but also the reserves that might have to be made for warranty claims during that period. And also understanding the appropriate point to transition those packs into a second life application. So around the remaining residual value of the vehicle and the residual value of the packs in other applications.
Yeah, no, it's a huge area, that, and I think it's one of the biggest money things floating around in battery modeling is that extraction of the value for as long as possible on the warranty issue. It's an enormous subject. something that, you know, I've wondered about in terms of providing connections. You know, what is the minimum amount of information you need to harvest to drive an accurate model on the other end? So there may be some things to do. Great. Well, thank you very much for that input. And then turning to you, Steve, then from your point of view, what's the next thing to do in terms of?
Yeah, so one of the things it's that we've currently been looking at is, as we've transitioned to manufacture, we've obviously noticed that there's quite a bit of variability in the cell performance in certain parameters. This is in the past being sort of covered by grading the cells, which has a sort of knock-on effect on the sort of profitability effectively of the operation. And you mentioned machine learning early on. One of the areas that we would like to cover is predicting from the tolerances of the individual components what the performance of the cell is at certain production rates and certain runs. And you know, we've noticed certainly with the work we've been doing in the BIC that, and it seems obvious, but you know, the higher the production run, the more information we gain, the more knowledge we have on the variability. But what we'd obviously like to do, and it's a far lower cost route, is to predict all that up front, so we don't have to make thousands of cells and tens of thousands of cells to achieve that performance. So that's something that our modelers are currently grappling with at the moment. So you know, any support on that side would be greatly received.
Yeah, well, certainly turning a single parameter into some kind of spread, a statistically distributed spread. So I guess the sort of Monte Carlo analysis, I guess, that you see in things like SPICE, you know, whether that's a direction that we might go in future. Is that spread information something you might even provide to customers, do you think, with appropriate protections of your information?
Possibly, I'm not sure. Yeah, possibly. Yeah, like you say, in terms of you know, the approach to grading, that would certainly be an alternative, effectively, and as data that would be shared.
Very good. Okay, well, thank you all. And then turning finally to Monica, I've hopefully teed you up for MSM2 now, because one of the interesting dynamics we have with this, you know, this inventive standard body that we have at the moment is that Faraday itself is obviously still investing in research in this area, and there's still some very active contributions coming from Faraday funded researchers, and maybe plugged directly into the standard. I almost think the standard itself might become another dissemination channel for the research that Faraday is funding. So in terms of what you've heard, what can we expect from MSM2? And do you think there are some real nice synergies there coming through, or are other things that haven't been mentioned yet, perhaps?
Yeah, absolutely, Peter. Thank you. Definitely the two you mentioned initially, the three-dimensional thermal coupling with the electrical. We know now that this is very important, especially for large form factor cells, and a lot of the industry seems to go in that direction, and especially for prismatic form factors where cooling is not necessarily very effective. One addition that we are making for the new multi-scale modeling is that alongside PyBAM, we are introducing reduced order models. So we're going to have equivalent circuit network models and equivalent circuit network models that are improved with physics knowledge that you can run and compare in terms of speed and accuracy and trustworthy with the physics-based models in PyBAM. And that's hopefully going to also provide a platform then as an alternative to look at systems with multiple cells. So going beyond a physics-based model for one single cell, and now allowing a module or a pack to be electrically and thermally coupled. And the other direction you mentioned, degradation, I think we are sort of knowing what we're doing now as a community. But we are also understanding how important is the coupling between the degradation mechanisms. So long gone are those days where you would just cycle a cell and attribute its entire degradation to a solid electrolyte interface, just because we know that happens. We now understand that as you use the cell at various stages in its life, different degradation mechanisms play a role, and you need to be aware of those. So this is coupling of degradation mechanisms within the 3D and thermal models is very much the focus. I wanted also to touch upon what Rob was saying about the procedures for testing. I think those are very important. So a lot of the numbers on the standard list of parameters that are needed for these physics-based models are actually very difficult to obtain and don't necessarily correlate to the measurements you would do or difficult to measure. So a focus for the sake of these models being usable in industry on both inputs and outputs that are measurable and that have been standardized, the test procedures for obtaining those values, I think is very important, because we know that anything on the test rig that its thermal boundary conditions affects the measurement you get. And so if what you're building is a pack with bottom cooling, then probably experiments from thermal chamber are not giving you the right answers. So having standard test procedures for both parameterization of the models and validation of the outputs of the models, I think it's something that BPX could look into it and would be very valuable. And then talking about what Stephen was mentioning with a statistical spread, I think that's an area that is more recently developing in terms of doing physics-based modeling about manufacturing effects and formation cycles effects. And that is very much possible with a physics-based model. I would say a lot of validation is required of those models, and it's only through direct collaboration with the industry that makes those cells that we can gain trust for that type of usage. And maybe just one last remark, that I think that fast enough condition that you have imposed is very challenging when you start adding all of these elements together. So there's a lot of work that can be done. The model we currently have is relatively fast. However, if you start thinking about three-dimensionality, coupling of degradation, systems of multiple cells, and so on, it's a different level of computational efficiency that you require. It may simply be that you can't put these models as they are together and expect them to work, but you have to have optimization layers in them to tell you to what level of discretization you need to go for a requirement on speed that you have imposed.
Yeah, I mean, it's something that we wondered about. I mean, certainly the 10 to 100 times seem to be a good working number from industry. That's where virtual prototyping is useful. If it's less than 1 times, it's not very useful. They'd rather go and build it. But yeah, absolutely, there's a huge challenge. The more detail you put in, the more computationally intense it is. So some strategies about where do you need the detail for this particular simulation and where you can forget it or desensitize it dramatically and just concentrate. The answer will depend on what you're trying to do. So there may be some methodology questions that come along later on. Okay, well, thank you. That's all been a fascinating and broad discussion around all the different places we could go. I just want to wrap up this part of the discussion. I think we've got some next step slides, and then we'll come back to your questions. I'll flash to that. So that's just going to be the next few things. So I said in this session we weren't going into the technical detail. That's coming on 11th of January, and the authors of the standard will be in a webinar to really give you the details and the philosophy about why we're doing what we're doing and why they come up with the answers that they have. Do go and look at the website, please. If you're do look at the latest briefing paper that covers modelling. I think has just been published by Faraday Institution. Early in January as well, there's an IMSI organised, which I remember as the Institute for Molecular Science and Engineering. There's another round of detailed modelling work or presentations coming from some of those who contributed to the MSM programme. That's coming on the 6th of January. And last of all, as you've heard, we're interested in your feedback. We're interested in potentially moving this on to a standards organisation of some kind. So if you'd like to be part of that or have some opinions on it, then do email us on bpx@faraday.ac.uk or use the Get Involved tab on the website. I think that slide's going to stay up once I fly back and stop sharing. So really, I think just thank you to our panel. Thank you for time and consideration an awful lot of information shared there, and a lot of stuff to digest as we look forward. But it's good to hear that this is, looks like it's going to be a useful initiative, and also that there's an awful lot more to do with it yet. Okay, so I think I shall stop sharing, and I think Sophia will share, and we'll move on to the questions. So let me just, this is the moment where I'm just digesting. So perhaps one, I guess touching on the subject a few of you have brought up in terms of what's the evidence for validation? This question, I think Rob touched on it first, of how did you get those numbers and how do you know it's right? So James Mason here is asking, I'd be interested in the work performed in correlating model predictions with real cell data, together with how actual measured data is then used to refine the model. So obviously these models are built based on, quite often, on terms of real cells or prospective production cells, Steve, if that's where you're going. It's an interesting question for us in terms of BPX. To what degree do we mandate certain ways of doing parameterization, or do we leave it as free space for innovation? But we are trying to cultivate best practice in terms of vendors, cell model vendors, presenting the basis for their the validation testing they've run on a model. What have you done to prove it? What kind of scenarios have you tested it against? Why do you believe it's accurate? So again, not mandating it, but really encouraging a good practice for sharing. So this question of correlating model predictions with real cell data. I mean, perhaps Monica, you're probably closest to this to start with, and I guess we were just discussing that at the end of the panel session there. So, in terms of how we go about that, I mean, you were talking about standard tests and standard ways of doing this. I mean, perhaps you want to enlarge. You have a chance to enlarge on that for a few minutes.
Sure, Peter. Thanks. I think that's, in a way, cultivating sort of analytical and rigorous thinking, being very aware of the hypotheses that you have made in building the model, acknowledging of the fact that the model will never be 100% a digital twin, and not sort of expecting it to perform well in areas where you know it shouldn't. If it doesn't perform well in areas you know it should, then that's when the research starts in identifying whether it's a mechanism problem, you haven't included a physics causality, or whether it's a parameter value problem that can be found through a sensitivity analysis. We do that as a daily work, and I reckon some of the industries or the representatives do this type of work as well to some degree on all of the models they build. One thing I would say is, even if we do see a model perform well, there is always the opportunity to stretch it in terms of the operating conditions under which you test it, in order to identify whether it still performs well under, let's say, the highest temperature gradient you impose on it, or the largest current you impose on it, and testing the boundaries of trustworthiness for it.
Okay, thank you. Anybody else want to comment on that?
Yeah, maybe I'd just agree with what Monica was just saying, really. I mean, I think part of the problem we see, because we buy access to certain cell libraries and have, what are some current versions of these type of models. And what we can see is that really the way that they've been built, the way that they've been informed is through a sort of limited range of testing. And so some of the questions that we want to ask essentially falls outside of even the extrapolation of the data that's been used to form these models. And that's where we sort of have issues. So an important point for us.
Good. I think we've got time. I mean, very little time left. Nobody's going to argue. I'll go for one more question very quickly. But this is one. This is James again, James Mason. So apologies that James has got all the airtime here. But this is a question that I rather like. So a colleague of mine brought up the analogy of SPICE in analog circuit design. That you know, early on, there was a massive discussion around what simulator, and that industry has moved into what's the model, you know, and that's pretty much what you expect of your semiconductor device vendor now, is they can provide the SPICE models, which have got manufacturing spreads, they've got all kinds of details about that stuff in the model, and that's really where all the conversation is. So do you think, I mean, battery modeling is a fabulously difficult thing, as I've discovered. I'm new to this world, but lithium-ion batteries are some of the most hideously complicated things I think I've ever come across. Will we ever get to the point where, you know, we move to that kind of SPICE-like model where manufacturers provide the models and we just pick it up and carry on and do our day job? Anybody like to start on that question? I could start with the one manufacturer present. Maybe I'll start with Steve, which might be a bit unfair.
Yeah, it's an interesting one, and like I said, certainly at the moment we would share in terms of our relationship with the end user and you know, what we see going forward. But I mean, I can't see why that wouldn't be the case. Like I said, that industry is a very competitive industry. It's you know, adopted a process that is a robust. So I can see that you know, downstream that would certainly be adopted by the cell manufacturers.
Well, that's great to hear. So if the manufacturer is going to do it, it should be easy from there on, surely. So Rob or Pete, or even Monica, would you like to comment on that point? Is that nirvana from your point of view, Rob and Pete?
It definitely is. It'd be interesting to see how this plays out again.
Well, that's part of what we're here to try to make happen, I guess. Anyway, okay, I have overshot.
I can say that it's definitely going to happen, but I think battery manufacturers need some help from initiatives like this one to inform them under which conditions sort of the testing needs to be done for those models to be worthy, and also in some areas of battery manufacturing, such as solid state, I don't think we know enough about the ultimate solutions to the chemistry challenges in order to now give such transferable models.
Okay, well, I think I've overshot by a minute, but thank you. That's a very high note to finish on. I think that we're heading for nirvana, where we all get the models that we want. They'll be calibrated correctly, measured correctly. We can be entirely confident in them, and everything should get so much simpler from there on. And I say, hopefully BPX can play a part in that, in terms of getting to those sunlit uplands. So thank you again to our panel. Thank you all for giving the time. Thank you to everybody who's attended. Hope you found that interesting. And again, just to reiterate, we're very interested in your feedback on this whole initiative. You have that nirvana destination now laid out very clearly. So it'd be really interesting to see what a broader population thinks of that and how we might get there via something like BPX. Okay, so thank you very much for now. Good afternoon. Hope you found that useful. And hopefully we'll see you on January the 11th for the technical deep dive. Thanks again.
Thank you.
Bye.